Hello, this is Guillermo Campitelli, and in this video I'm going to talk about the within subject design, still in the case in which we have two nominal variables affecting one numerical variable, and in the case of the within subject design there is a change in the variables. In one of the variables, so we still have the match variable, but instead of have color, we have the number variable. So I explain. We've got a sample of 80 participants, and the variables are number, and we have one value is low and the other value is high, and the other variable is match, which is what we had before, whether there is matching or not between the color in the presentation or the learning phase and the recognition phase. So the variable number now is the number of so the number of objects in the landscape. If the number of objects is on average 8, we call it a low object landscape, and if the number of objects is around 18, is a high number of objects. So because color didn't affect, so all the images on the learning phase were color images, and so then some of them matched, so they have the same color in the recognition phase, and others were black and white, so no match. Okay, so and the causal model identifies that there are other variables that may affect not just number and match, and these are variables that we don't know, and let's continue. So because we have two variables with two values, then there are 4 conditions combining the two variables, and the 80 participants will go through the 4 conditions. So condition 1 is low number of objects and no match. Condition 2 is low number of objects and yes match. Condition 3 is high number of objects, no match. Condition 4, high number of objects and match. Okay, so let's go to the descriptive statistics, and we, as in previously, we can have statistics about the conditions and about the variables. So let's use JASP, descriptive statistics, and these are the rules that we are going to follow. Now the file is the repeated measures file with SPSS format. Oh, sorry, I just opened a new one. Sorry about that. Here is the new one, and you can see that we've got reaction time 1, reaction time 2, reaction time 3, and reaction time 4, and we've got participant 1 to 80. Okay, so let's ignore the other variables. Okay, so we go to descriptive statistics, and we drag the RT1, RT2, RT3, and RT4, all the reaction times, and here we've got descriptive statistics. In statistics we can add, we tick for more, standard error of the mean, typically useful to do the estimation of parameters of the 95% confidence interval, and in plots we can do the box plots or the violin plots or the jitter element, so the data, the raw data jittered. And so these are the descriptive statistics. Then here we have the graph that I did it with R. So condition 1, low number of objects and no match, low number of objects and match. That was condition 2. Condition 3, high number of objects, no match. Condition 4, high number of objects, yes match. And these are the data. So this is the mean in green, the mean of each condition. The black line shows the mean of the here low number of objects, and this black one the mean for the high number of objects. And the yellow lines or the orange lines, this is for the no match, and this one is for the yes and yes match. So you can see that it's an important, very important difference between the high versus low, but the difference between match and no match is not as big as the other difference. And here we can hint to an interaction. So basically, if this violin plot would be here, if the violin plot were here, then we'll have a clear effect of high versus low. But here we've got this change that makes us think that there is an interaction. So basically the effect, the difference between high and low is going to be different in the no match than in the match conditions. So let's see in the analysis. Okay, so then those were the data in each condition, the mean, standard deviation, and this is the mean and standard deviation for each value of the variable. So variable number, low, this is the mean and standard deviation, high, mean and standard deviation, and for match, no match and match. So you can see that the difference between match and no match is not big, around 24 milliseconds, but here is more, so a bit less than 200 milliseconds. So let's see now parameter estimation. We are going to see the traditional frequentist approach, the Bayesian approach, and resampling. Okay, let's start with the traditional parameter estimation, and again we can estimate the condition means, the difference between conditions, and then when considering the variables, we compare the values of each of the variables, and we also estimate the mean of the values of each variable. So basically we use, as I showed you when we were seeing the descriptives, I told you we can take the standard error of the mean, and we obtain the standard error of the mean for each condition, and by hand we calculate the lower bound and upper bound of the confidence interval. So basically these are the estimation of means with confidence intervals for the 4 conditions. Okay, so now for the difference between the conditions, we have to do a trick in JASP. So basically we have to do a t-test, repeated as paired sample t-test. Okay, let's just go to t-test and paired samples t-test. That's what I meant. Okay, paired sample t-test, and what we have to do is to put all the pairs. So RT1, and it will generate this, and then we are going to compare to RT2. So these are condition 1 versus condition 2. Now condition 1 versus condition 3. Then condition 1 versus condition sorry, I missed that one. Condition 1 versus condition 4. Then condition 1, no, we did already all the ones with 1. So now condition 2 versus condition 3, condition 2 versus condition 4, and finally condition 3 versus condition 4. Now we in additional statistics we put location parameter and confidence interval. So basically we got what we wanted. We got here for the comparisons between conditions. We ignore the t-test, degrees of freedoms, p-values, because we are not doing any hypothesis testing. We are interested in the parameter estimation, mean difference, standard error of the difference, and the lower and upper bound of the 95% confidence interval. So that's what we were after. Okay, so here are the results. Okay, now we have to do. Okay, so now when we talk about the variables, not the conditions, then we need to do estimation of the means and the differences of mean reaction time between the two values of the independent variables. So when here we compare the number low to high, and sorry, there is no comparison there, it's just the estimation of the mean and mean reaction time in the population, and for match we also did the same estimation for the values no and yes. It turns out that it's quite tricky to do it in JASP or Jamovi, but this is quite easy to do. You can do it in Excel, just calculating the mean standard deviation, and then by doing that then you calculate the standard error and confidence interval by hand, as I explained in previous videos. I did it with R, but you can do it that way. There is a way of doing it with JASP, and that way is to use a different database entered the way I explained in previous videos, instead of doing the SPSS way, to do it not to use one row per participant, but use the columns as variables, and it's very easy to estimate the mean of the values of the different the means of the values of the different independent variables, but we don't really need to do it, so I just did it with R, but it can be done with Excel. Okay, so here we've got the estimation of the means and of the population, and we do the parameter estimation of the mean differences. And basically the way it's done is when it's doing the ANOVA. When we do the ANOVA, we we get the standard error of the differences in the post hoc analysis, and this will be explained when I explain the NHST. Okay, so let's move to Bayesian parameter estimation. We are going to use R, or I use R to do the parameter estimation. So we start with what we are going to do is to estimate the means of the population of reaction time in each condition, each of the 4 conditions. and then we are going to estimate the difference among those conditions. So basically we have 6 contrasts, and we estimate how they would contrast the means in the population. So for that we need a prior over the mu's, which are the means, and it's a flat prior, an informative prior, so basically any value is equally plausible. So I will briefly explain the hierarchical model. The I plate, things inside this plate repeat 80 times. Things inside the J plate repeat 4 times, and things inside the K plate repeat 6 times. Things outside the plate do not repeat. So basically I represents the number of participants. There were 80 participants, and J is the number of conditions, 4 conditions. So we are going to have the mu is the parameter that we are very interested in, J. So we've got 4 mu's, and delta K we have is in the K plate, so we have 6 deltas. So the mu's will represent the means of the conditions, and the deltas will be the difference, the contrast between the mu's. And so basically the probability of the data, or probability of values of reaction time, are normally distributed with a mean of theta, and we've got 1 mean per participant, because we've got not only per participant per condition. So because these two are both in the I plate and the J plate, so they repeat 4 times 80 times, so that's 320 times. So we've got 1 reaction time, so we have 320 reaction times, and we have 320 thetas. So we determine the probability or likelihood of each possible value of reaction time with the normal distribution with theta as mean. And where this theta comes from? Well, it comes from the mu of the condition in which this score is located. So basically the mean of the condition will influence the theta here, and gamma is a precision of the normal distribution. Remember that the statisticians that developed the software, they use precision instead of standard deviation like we use more in psychology. So but the prior is over the standard deviation. Here pi represents standard deviation, so the prior, which is a uniform distribution that goes from 0 to 100, which is an informative prior, and it's over the standard deviation, and the precision is 1 divided the standard deviation squared. Okay, so that's where this theta comes from, and that normal distribution that determines the probability of the RT values or reaction time values has also a precision, which we'll call tau, and the precision is determined by the standard deviation, and the standard deviation has a prior that goes from 0 to 100, again an uninformative. And finally the mu has a prior, which is a normal distribution with a mean of 0 and a precision very, very low. So if the precision is very low, that means that the standard deviation is very, very high. So it's a very flat normal distribution. Again, is an uninformative prior that gives equal plausibility to each value of mu, and actually that's that prior I showed in the previous slide. So we use Markov chain Monte Carlo simulation method. Obviously a software does that for us, and we obtain the posterior distributions of the mu's. Remember, the model has 4 mu's, 1 per condition, and here are the posterior distributions over the one for condition 1 is around 500. Here we've got the mean of that distribution of 500, and values are around 500, so we are pretty precise estimation of the mu. Same for condition 2, the distribution mean is 449, and that the confidence interval we are saying that is between 444.9 and 454.1, so pretty narrow interval, so it's a very good very precise prediction estimation. And for condition 3 and condition 4 we cannot differentiate, they are they overlap, and you can see the mean of mu3 is 6 distribution is 647.6, and the one for 4 is 650.2. And now we've got the deltas, so the model has 6 deltas, and here are the deltas, which are the contrast between the conditions, so there are 6 contrasts, and here are the posterior distributions of the differences between conditions. So here, for example, we got the condition 1 versus condition 2 it has a mean of 50. So it's this one, we've got delta 1, 2, this distribution. Condition 1 versus condition 3 is has a mean of minus 146.9, so it is this distribution, that's the color, delta 1, 3. And delta 1, 4 we cannot see it because it's overlaps with delta 1, 3. Okay, so we've got the 6 distributions, but some of them overlap due to the fact, and I'm going back, due to the fact that the distributions condition 3 and condition 4 are very similar. So when we do all the comparisons, condition 3 are going to be very similar to the ones that compare to condition 4. Okay, so that was Bayesian estimation. Now parameter estimation by resampling, and there is nothing new here. What we do is to resample from each condition. So we've got 80 values in each condition, and we produce new samples of these 4 conditions, and in these new samples we obtain the mean of each, and we obtain the mean differences, so the 6 contrasts and the 4 means, and we do that several times until we can have a distribution of means and mean differences. This is an example that is the distribution of condition 3 versus condition 4, and here are the other comparisons, the summaries of the distributions, sampling distributions generated by resampling.